In our previous note, we saw that anytime something changes its temperature, we can actually calculate how much heat is being gained or lost in that case, how much thermal energy is being gained or lost. But if something changes its state when that happens, if it changes, for example, from a liquid to a gas, we need to actually define a new value called the latent heat. And it's a little bit easier to understand latent heat if we actually look at a graph and imagine a specific example. So if we take a look at this graph, let's imagine that it's representing, let's say, a block of solid ice, so just regular frozen water, that we put in a beaker on a hot plate. And so what that hot plate is going to do is add more and more thermal energy over time. And so at the bottom, where you see energy input, that's representing more and more thermal energy being added as it's sitting on the hot plate. And then what we can do on the y-axis is track its temperature. Look at how the temperature of that substance will increase. So again, if it starts as just solid ice, it's going to be at a very cold temperature, and as we add more thermal energy to it, it will increase and begin to go up the graph like so. But at point B, something very special would happen. So if we're dealing with ice, like water specifically, what would happen at point B is that ice would suddenly get to 0 degrees Celsius. So it would start in its solid form below 0, and then when it gets to point B, it's getting to 0 degrees Celsius. When that happens, of course, the ice is going to melt. It's going to go through a phase change. And what's interesting about that is there's a period of time, specifically this flat period here from B to C, where we actually notice that even though we continue to put more energy in, because it's still sitting on the hot plate, there's a period of time where the temperature actually won't change. That period of time is when it's absorbing what we call latent heat. So that latent word kind of means like hidden or stored away in a way that you almost wouldn't notice. That's what that word latent means. And so latent heat is energy that's being stored away in a way that's not actually increasing the temperature of the substance. So there's this period of time from B to C where that ice is being melted into liquid water. But then eventually when it gets to point C, suddenly it will fully be water, liquid water, at 0 degrees Celsius. And from there, we'll continue to add more thermal energy, and we'll get a hotter and hotter liquid. But then eventually something else special is going to happen at point D. Point D would be specifically 100 degrees Celsius. And of course, we know what happens with water when it gets to 100 degrees Celsius. It reaches its boiling point. It starts to vaporize or turn into water vapor, a gas. And so once again, we'd see another latent heat situation where there'd be another brief period of time where we're putting more thermal energy in, but it's actually not increasing the temperature of the substance. It's just absorbing that heat. And what it's actually using that thermal energy for is to break apart the intermolecular bonds that hold it in a certain phase. So if the bonds were holding it together in liquid form, a lot of that latent heat is being absorbed and helping to break down those bonds into more of a gaseous form. Eventually, though, we'll end up with all water vapor when we get to point E. So it'll be all in the form of water vapor at 100 degrees Celsius. And then from there, we can take that gas and continue to heat it to a greater and greater temperature in the form of steam. So that's the idea with graphs like this, is they help us to understand that even though we might continuously add thermal energy, there will be specific points in time when this graph of temperature will actually flatten out. Because when the latent heat gets absorbed, the temperature does not change. So when we calculate how much thermal energy would be required to change something up to a certain temperature, we also need to think about, is it changing state? And that's an important factor that we need to deal with. It turns out we have a fairly simple formula for calculating latent heat of a phase transition. And remember, phase transition is just a fancy term for changing its state. But we actually need to specify if it's what we call a latent heat of fusion, which means when we're changing something from a solid to a liquid, or actually vice versa, or the latent heat of vaporization, which is the amount of heat being absorbed or released when we change something from a liquid to a gas, or vice versa. But the formula itself is quite simple. It's just telling us that Q is equal to the mass of the substance multiplied by L. And L represents that latent heat value. But again, it could be for vaporization or for fusion. So for here, when I'm saying a few examples, what I mean is that there are actually two different versions of this that we sometimes write. So we could write LF for the latent heat of fusion, which again is solid to liquid, or you can maybe add an arrow going the other way. It's also going back the other way from liquid to solid. We use that value anytime it's a solid liquid or liquid to solid transition. But the other kind that we sometimes use is called LV, latent heat of vaporization. And that's for when we're changing something from a liquid to a gas, but we can also use it to figure out how much energy is released when we go from a gas to a solid. So you might want to add an arrow up there that goes the other way. From there, all we have to do is use our formula that says that Q is equal to mL. We also need to be a little bit careful about how we use it. So specifically, this version of the formula that says Q equals mL, this is for heat being absorbed. And that's going to add positive energy to something, and it'll heat up as it absorbs that thermal energy. But actually, we can use a different version of this, and we just put a negative sign in front of it, and use the exact same formula other than that anytime we're dealing with heat being released. So if it's heat being released, we know that it's something cooling down, giving off that thermal energy. So for example, if I was dealing with a transition from a solid to a liquid, I would use Q is equal to M times LF, latent heat of fusion. But if I was going the other way, I would still use latent heat of fusion, but I would use negative M times LF. So that's just something we have to remember. Now, we can also see that in order to make all the units work, latent heat must be measured in joules per kilogram, because it literally means how many joules of energy do I need to change the state of a certain number of kilograms of a substance. So it's in just joules per kilogram. So make sure you're keeping your units in that form. Those latent heat values are in some ways similar to something like specific heat capacity, or even kind of similar to something like coefficient of friction. They're things that aren't exactly the same for every substance or material. They're things that we actually have to do lab tests on to determine what they would be for each different kind of substance. And so those aren't things that you would necessarily have to know off the top of your head. They would be things that even scientists would just look up either in tables, in books, or just online. And so this table is an example of something that you might find online to provide information about the latent heat of various substances. So there's a couple things we need to be careful of in a table like this. First of all, this is similar to most tables you'll find online, which often measure these latent heat values in kilojoules per kilogram. Remember, normally latent heat would just be measured in joules per kilogram, but because all of these values are typically very high, to avoid having to write so many zeros, they show how many thousands of joules per kilogram it would take. Also notice that there's two different versions of it. There's latent heat of fusion, but there's also latent heat of vaporization. And most tables will also include something about melting point and boiling point, because it's important to know what is the special temperature when that latent heat is going to become a big factor. We of course know for water it's fairly simple. The melting point is 0 and the boiling point is 100. But we have to be very careful if we're dealing with another substance, because that might be very different than the melting and boiling points of water. With this new information about latent heat available to us, we can now solve similar problems to what we've done before, but also include situations where the state might change. So for example, if we want to know how much heat would be required to take 2.5 kilograms of water that's at 20 degrees Celsius and turn it into steam that's at 150 degrees Celsius, we have to remember that that's going to require a change of state to occur. So there's actually going to be a few different pieces to this calculation, and to understand why there's different pieces, it's useful if we sketch a quick graph first. So it doesn't have to be a very detailed graph, but this kind of graph is something I'd recommend that you sketch in all kinds of questions like this that involve latent heat in some way. So I tend to call these QT graphs, because the two variables that we're going to use are Q and T. So Q is along the x-axis to represent how much thermal energy we're adding, and T is going to be our y-axis to track what's happening with temperature. Very similar to the graph that I showed you when I first discussed latent heat. And then we should mark off a few key points in temperature. Again, this is just a sketch, so it doesn't matter how precise we are on our axis labels, but we should mark off a few key points on the temperature axis. For example, we'll say that down here is 20 degrees Celsius, and that's where it's going to start from. We also know that at the very end, we want it to be at 150 degrees Celsius. So I'll put that towards the top. But those aren't the only two key points, because we know something very special is going to happen to this water when it gets to 100 degrees Celsius, which I'm going to label right around there. At 100 degrees Celsius, it's going to not absorb any thermal energy that changes its temperature. It's going to be absorbing latent heat. And so our temperature actually won't change for a brief period of time when it gets to 100 degrees Celsius. So if we sketch out what would happen, well, I add thermal energy to this 20 degrees Celsius water, and it steadily increases all the way up to 100 degrees Celsius. And then it's going to level off for a while from there as it absorbs latent heat, and then eventually when it's all converted into steam, it's going to increase from there until it gets to 150 degrees Celsius. So what this is telling us is that we actually should divide up our calculations into three separate steps. If we look at this first piece of the graph where it's increasing, well, that's involving a temperature change. And so we can solve that question just the same way that we use that formula to solve the glass in the greenhouse question in our previous note. We can also do the same thing for what I'm going to call stage 3 at the end. Again, it's a situation where the temperature is changing. So we can use that Q equals mc delta T formula that we've used in our previous note. It's this middle section here, which I'll call section 2, where we're going to use a different formula, the new one that we just learned in this note, the latent heat formula. So we're going to break this up into three separate pieces, calculate them all separately, and then come up with a total amount of energy by simply adding them all together. So there are a few other things we need to state that we know. First off, right away in the question, it mentions that it's 2.5 kilograms. We also know the specific heat capacity of water. Now, this isn't something I discussed in previous notes, but if this was ever needed in a test question, I would always give it to you. But for reference, the specific heat capacity of water, so I'll put a little W beside the C there so that we know it's the specific heat capacity for water, it's about 4184 joules per kilogram degrees Celsius. Remember, that was the unit that we had for specific heat capacity. And we also need to know a latent heat value. So we need an L, but we need to think about, do we need the latent heat of fusion or the latent heat of vaporization? And in this case, we've got something that is vaporizing. It is changing from a liquid to a gas. So we want LV, the latent heat of vaporization. From there, we just need to look up in any charts or tables that were provided, what is that latent heat of vaporization for water in this case? Well, I've actually left the bottom of the chart available for us to see. So the latent heat of vaporization side of things is this value here. But we need to be extra careful because that 2260 is in kilojoules per kilogram. And I need to make sure that all of my calculations are in joules because in the end, I want a final answer that's in joules. So there are different ways you could write it. You could just add 3 zeros to that if you wanted to. I'm going to use a bit of a fake scientific notation way to write it. So I'm going to just write it this way, 2260 times 10 to the 3 joules per kilogram. And that's my way of saying it's really 2,260,000 joules per kilogram, or about 2,260 kilojoules per kilogram. Either way, it's saying the same thing. And so in the end, what we really want is a value for Q. Remember, we're going to break this up into 3 separate steps that I'm going to call Q1, Q2, and Q3. And then we're going to add them all together to find Q total. That's what we really want to know, the total amount of energy when we put it all together. That's going to be our final step, is to put it all together. So now, as I said, we just have to break this up into different pieces and calculate them all separately. So our first step is just going to be to find Q1. And because the temperature is actually increasing, we are going to just use the formula that we used in our previous note, Q equals mc delta T. Well, the mass is 2.5 kilograms, 4184 is the specific heat capacity, and then we need to be really careful for the change in temperature. I can actually subtract the numbers right here in my equation if I want to. Remember that it's not going all the way from 20 straight to 150. In this first stage, it's going from 20 all the way up to 100. And then we have to stop there because something new is going to happen when it gets to 100. So we really just want to know what's the change in temperature when it goes from 20 to 100. Well, you can probably work that out in your head, but a way we could also calculate it or show our calculation is to take 100, our final value, and subtract 20. So that, of course, gives us 80, and then when we calculate all of that together, we get a great big long number. It's 800. That's how many joules of energy it would take to increase the temperature by that amount. If we want to do step 2, what we're trying to find is what I would call Q2. Q2 is where we have to be a bit careful, though, because now the temperature is not changing. So we actually just need to use the latent heat formula. So we just need to multiply the mass of our substance by its latent heat value, but remember specifically its latent heat of vaporization because it's changing to a gas. So it's really just two numbers we're multiplying then. And to save myself some room, I'm going to write it beside. So it's going to be 2.5 for the kilograms, and then multiplied by 2260 times 10 to the 3 to make sure it's 1,000 times bigger than the number I saw in the chart. And when I do all of that, I get 5,650,000 joules. So you can see that's a huge number of joules. Over 5 million joules, actually between 5 and 6 million joules of energy. Which if we compare that to how much energy was required in the first stage, you can see it's much, much more. And then our final step, actually not our final step, but our second last step is to find Q3. And in Q3, or stage 3, now it's increasing its temperature again. So we go back to the formula that we use when something's increasing its temperature, MC delta T. Specifically in that case, it's still 2.5 and still 4184. Those didn't change because we're still dealing with 2.5 kilograms of water. But now the temperature change is different. Now it's going from 100 all the way up to 150. So we take our final value that we have, 150, and we subtract 100. And we know that that difference there is 50 degrees. So that change in temperature is 50 degrees. When we multiply all that out, we should get 523,000 joules. So now our final step, what I'll call step 4, is to find Q total. And it really is just Q1 plus Q2 plus Q3. So we plug in the three values that we found so far, 800, plus the very big one, 5,650,000, and then 523,000. When we do all of that, we get 7,009,800, or approximately 7.0 times 10 to the 6 joules, or about 7 million joules of energy. That is what we found in this case.